Okay, physics friends, welcome back. We're going to look at a FT graph today and use it to answer 3 different things. So first we're going to look at what the impulse is for this object. Second, we're going to determine the object's new speed. And last, we're going to see what the average force was applied to the object. So if you take a quick look here at my FT graph, I can see that the force varies as time passes. So it's not as easy as just picking off a point and saying, oh, well, that's the force, and I'm going to multiply it by the time to get the impulse. Because impulse, remember, for part A, impulse, or J, is equal to F times T. And that's true. This is the average force, though, and my force varies. So another way I can find impulse is to know that the units for impulse is newtons times seconds. And when I look at this graph, the area of this shape is going to equal the impulse. Because the units are newtons in seconds. So newtons times seconds gives me the area here. Okay. So I'm going to use the area. And because this shape is a triangle, I'm going to use the area that's going to equal the impulse. And so I'm going to look at 1/2 base times height. Okay, so J is going to equal 1/2. The base is, careful, 0.1, and the height is 100 newtons. Okay, so this ends up being J is equal to 1/2 of 50. Nope, I'm sorry, 1/2 of 10. Hello. And so then J is equal to 5 newton seconds. Okay, so there's my impulse for part A. And then I can actually use this information to help me solve B and C. So for B, it's asking what the new speed is. Well, I also know that J not only equals F times T, it also equals M times a change in speed. So I'm going to use J is equal to the mass times a delta V. So I have my impulse, I have 5, and then that equals my mass, which is 2 kilograms. And then delta V, that's a V final minus a V initial, which is 5 meters per second. So if I divide by 5, 5 divided by 2, and then I'm going to add 5. So I have 5 divided by 2 is equal to V final minus 5. And so 5 divided by 2 is 2.5. And then I'm going to add the 5 to the other side, which leaves my new speed as 7.5 meters per second. Okay. Now a couple points though. Be careful, because this is a positive impulse, because the area is a positive area. If, for example, you had an area or a triangle that was underneath the time axis, this is going to give you a negative J. And if you have a negative J here, say you had a negative 5, this would be a negative 2.5 plus 5, so your final speed would actually be slower than your initial, which means that the object would be slowing down instead of speeding up. So just be careful with the area, whether it's a positive J or a negative J, a positive impulse or a negative impulse. Okay? And then the last part here that we'll talk about is part C, which is asking for the average force applied to the object. Which is a little bit more challenging because, again, remember this force, it changes as time passes. But if I look back at my impulse equation, J is equal to the average force times the time was expended over. And so I can actually use the impulse, which is 5 newton seconds, and set it equal to the average force times the time of 0.1. And so if I divide 5 by 0.1, I end up with an average force of 50. Which is clearly not what the maximum was. But another way you can think about that is you're taking this shape and you're squishing it so that it looks like a rectangle. And when you So you're taking the top half and making it fit. And so the average force is always going to be in a rectangular shape, because then your force isn't varying as time passes. And in this particular problem, it's 50 newtons. Okay? But you can always find it using the J equals F average times the time. Okay? So hopefully that gave you a little bit of insight into how to use an FT graph to find what you're looking for or what the problem is interested in.